In this video, I'm going to check if the function f of z, which is equals to 1 divided by z, is analytic. So given that function there, f of z, we know that a function is analytic if it satisfies the Cauchy-Riemann equations. And the partial derivative of u with respect to x is equals to the partial derivative of v with respect to y. And the partial derivative of u with respect to y is equals to minus the partial derivative of v with respect to x. So in this case, I would have to write my f of z in the form of u plus iv. What we are given there, the z there, that's a complex number. A complex number, you can write it in the form x plus iy, where x and y are real numbers and I is equals to the square root of minus 1. So substitute this set here into our function f of z, then we have 1 divided by x plus iy. When we are looking at a division of complex numbers, we multiply the numerator and denominator by the conjugate. So we multiply the denominator and the numerator by the conjugate of this x plus iy, and we would have x minus iy divided by x plus iy multiplied by x minus iy. And that will simplify to x minus iy divided by x squared plus y squared. I can then go on and write the real part on their own, the imaginary parts on their own, and would have x divided by x squared plus y squared plus I multiplied by minus y divided by x squared plus y squared. So that's our f of z there. And when you compare it with this one here, we see that our real part there, this one, that will be our u. So we'd have u is equals to x divided by x squared plus y squared. And the imaginary part gives us the v. So we'd have our v is equals to minus y divided by x squared plus y squared. So we have our u, we have our v. We now need to check if those u and v satisfy the Cauchy-Riemann equations. So I'll start by evaluating the partial derivative of u with respect to x. Our u here is a quotient there, so we'll have to use the quotient rule. So I'll take this as my u, and then this is my v. So we'll have the partial derivative of u with respect to x will be equals to x squared plus y squared times 1 minus x times 2x divided by x squared plus y squared squared. And that will simplify to y squared minus x squared divided by x squared plus y squared squared. So we have our partial derivative of u with respect to x. I'll now go on and evaluate partial derivative of u with respect to y. So for the partial derivative of u with respect to y, I'll use the quotient rule again. And now I'm taking this to be my u, this to be my v, and differentiate with respect to y, treating x as if it's a constant, and we would have x squared plus y squared times 0 minus x times 2y divided by x squared plus y squared squared. And this will simplify to minus 2xy divided by x squared plus y squared squared. So that's the partial derivative of u with respect to y there. We now go on and look at the partial derivative of v with respect to y. So this is our v, it's a quotient. We use the quotient rule. So I will take this part here to be my u, this to be my v. Then differentiate with respect to y, treating x as if it's a constant. And we would have the partial derivative of v with respect to y is equals to x squared plus y squared times minus 1 minus y times 2y divided by x squared plus y squared squared. This will simplify to y squared minus x squared divided by x squared plus y squared squared. So that's the partial derivative of v with respect to y. I now move on to evaluating the partial derivative of v with respect to x. Differentiating with respect to x, treating y as a constant. So I'll use the quotient rule again, and the result that we get there is the partial derivative of v with respect to x is equals to x squared plus y squared times 0 minus y times 2x divided by x squared plus y squared squared. And this will simplify to 2xy divided by x squared plus y squared squared. So what we have there, we have our partial derivative of u with respect to x, partial derivative of u with respect to y, partial derivative of v with respect to x, partial derivative of v with respect to y. Now if we look at this partial derivative of u with respect to x and the partial derivative of v with respect to y, we see that those two are equal, so they are satisfying this equation here. So we have that one there satisfied. Now look at the following. The partial derivative of u with respect to y. There's a minus sign there. And the partial derivative of v with respect to x. What we see there is partial derivative of u with respect to y is equals to minus partial derivative of v with respect to x. So this equation here is satisfied. So what we are having there is those Cauchy-Riemann equations, they are being satisfied, so that given function there is analytic.